What I want to talk about here, though, more is the PID provider. As I said, at the moment when I walk up to a lot of production systems, I'm not finding the MySQL provider available, and so I'm using the DTrace PID provider to look at the internals of MySQL. If you have the MySQL provider, that's great, and if that can answer the questions you need, use it. Else you can try this. It's dynamic tracing. It is an unstable interface. Scripts may break between releases of MySQL. It works anywhere DTrace and the PID provider is available. To show the previous one-liner written using the PID provider, instead of having the convenience probes, MySQL query start and query done, I'm answering it by matching a function from the internals of MySQL called dispatch command. And I am tracing the entry to dispatch command to the return of dispatch command, and I'm doing the same timestamp and quantize for the distribution plot. There are wildcards around the dispatch command name because when it's actually compiled up, it looks something like this. It has all this junk around it. That's the C++ signature. If you run that through C++ filt or GC++ filt, it'll actually print out the type of the function. So we've got dispatch command, enum server command, thread pointer, character pointer, and an unsigned int. Or I can look up the source code, and we'll show that. So I'd like to do a few demos of this, and I'll start by, this is an idle system. And what I'll do is I'll list out all probes that are available for this version of MySQL. So there are 21,000 probes for this one. I picked an idle system to start with because I'm going to do something that I normally don't do, and that's I'm going to trace everything that this MySQL process is doing, just so you can see what it looks like. It's not actually responding to queries right now. It's a database that I've configured, but I'm not doing anything with yet. This probe definition, so DTrace -L will list probes. It won't enable them. If I drop the L, what this will do is it will enable those probes. It will go to the address space and change those instructions so that when those functions are entered, it will go and run a little bit of instrumentation and return. Do not run this on production. I've left those two middle columns blank, or fields blank, which means it's going to instrument everything. This is turning on everything, all 21,000 probes, and that's why I've picked an idle system. So that's the output. It's kind of scrolling. You can see how it is only printing every second, due in part to what it's doing, the process, but also due in part to DTrace is only gathering the information every second. Even though this is not a distribution plot, this is actually lines of output, it's still buffering that in the kernel. And then the command line DTrace utility is fetching it every second. I can change that. So I can do a DTrace -x, switch rate equals 10 for 10 hertz. And it's hard to see, but it is printing a bit snappier. You can see it waiting on pulses, though. That's how it's actually doing a sleep, how it's implementing a sleep. Let me do a little bit more with this. I'm going to add an action. So here I've said trace timestamp, and this timestamp is the high resolution timestamp we've got available. It's in nanoseconds, and so I can now see the time that each of these functions began. While I'm at it, I can put in the return probe. Now I can see the time that they were entered and returned. So you can imagine I can take this output and pick through it if necessary to find out where latency is by doing deltas. And I can turn this one line into a DTrace script and actually do those deltas in the script. Have the output printed immediately. But I just want to give you a very quick look at detracing everything to show everything that it can present. I'm going to add a -f, which is flow indent. This is something I only sometimes use when I'm working on real-world problems. Usually by the time I'm working on real-world problems, I have specific probes I'd like to instrument. So I'm not doing everything like this. I'm just doing this as a demo to show you the capabilities of DTrace. So while this will look really hot, it's not something that I actually use a lot. That's what the -f is doing, is it's indenting. As we enter functions, it will indent the output, and as we return from functions, it unindents the output, which helps me see the flow of the code, if I wasn't already familiar with that. It's great to get a quick understanding of the relationship between functions. So what I'm usually doing with DTrace, however, is I'm not tracing everything. Tracing everything, while the overhead of DTrace is minimal, if you trace everything, and I wouldn't run this on a production server because I may slow it down by 30%, 50%. I could even slow it down by 2x because I'm tracing absolutely every single function. In production, I pick the functions that I'd like to trace and then get that information out to answer problems. To give a short demo of that before I get into query latency, let me pick on OS thread sleep. So I'm going to add that to the probe definition. OS thread sleep. I guess now I don't need the -f for flow indent, so I'm just going to drop that. So now I can see that printing every second, and that resembles more likely what I'm doing in production is I'm picking a function I'm interested in and just detracing that. To learn more about the functions, like I said earlier, if it's not part of a book, I can go to the source code. Here's OS thread sleep in the source code for MySQL for this version. That's in innobase os0 thread.c. The first argument is a time in microseconds as an unsigned long int. And just to illustrate a little bit more about the capabilities of DTrace, I'll print that out. DTrace, apart from seeing the entry and return from functions, I can see the arguments to functions as well. arg0 is the first argument. And so here I can see, so the source code said that was microseconds, right? Okay, that's microseconds. So that's the value that's being passed to OS thread sleep. It's saying sleep for, that's 1 second and 5 seconds. This is actually printing out so rapidly, it's unlikely to be the same thread because we obviously didn't wait 5 seconds for the next line to be printed out. What I might want to do is print out the thread ID as well, so we can understand that a bit better. So there's a variable called TID. And so now I can see thread 8 is sleeping for 1 second, thread 7 is sleeping for 1 second, and it's thread 9 that's sleeping for 5 seconds. To find out how it got there, there's a great function DTrace provides called uStack, which provides the stack backtrace. So now each time it prints out a line, it prints out the userland stack backtrace of how it got to that function, the ancestry, and I'll Control C it because it will keep printing out. And let me find thread 9, there it is. So thread 9 is sleeping for 5 seconds. That was from OS thread sleep from server monitor thread. So if server monitor thread is sleeping every 5 seconds, thread 7 is server lock timeout thread. And thread 8 is the server error monitor thread. And I guess these are sleeping every second, and thread 9 is sleeping every 5 seconds. So just a very quick look at the capabilities of DTrace on a completely idle MySQL system. I find this pretty interesting. Even though MySQL is idle, it's not actually doing anything. I'm able to tease out information about what it's doing while it's waiting for work. What I'll do now is I'll actually demo something more interesting. So this is a production server. And I'll run a script I wrote earlier called MySQL dpid latency.d. And this is looking at the query latency as a distribution plot. When I hit enter, it instrumented MySQL, collected the data. When I hit Control C, it cleaned up that instrumentation, printed out the summary. Most of the queries are between, again, this is nanoseconds, so that's 131, that's 0.1 and 33 milliseconds. So these are getting a little bit slower than I usually like to see. I like to see them in the sub 1 millisecond range. This has caught some outliers as well. In fact, we've gone down as slow as 1 second. I'm very familiar with dropping the zeros. I've done this too much, but that's actually 1 second in nanoseconds. And we had 9 queries that took a second while I was tracing. I'll just trace that again. So that one's a bit better. I caught some event was happening earlier, but here I've got most of the queries are between 65 and 200 microseconds. That looks much nicer. Obviously, if I'm averaging the query latency, what would the average be for this? Well, thousands of queries happened with millisecond time and faster. Only 9 queries happened over 1 second. So these 9 queries may be lost in the average. But being able to print out the full distribution, I get to not miss out on any details. So that's actually, that script, and I put this on my blog so it's public. It's a short DTrace script. It starts with hashbang user sbin dtrace -s. And we're instrumenting dispatch command entry to dispatch command return. Dispatch command is the function that executes queries, and it's doing the timestamp delta and counting them. It's actually a very simple DTrace script, a good building block for adding other information. So I can extend this and add other functions from within MySQL or from the kernel so that I can compare them and do performance analysis. That distribution plot I was printing out, that was summarizing from when I hit enter to when I hit Control C. So there was 10 seconds or so was summarized as in one ASCII distribution plot. What we find is that distribution can change over time. So while it may have solved the problem of averaging the query latency itself, in some ways averaging the y-axis on this plot, we're losing information if it changed from 1 second to 10 seconds later because it's all bundled together and printed out. That's what these heat maps solve, because we see that distribution every second, and we can see if it's changing second by second. So with the right visualization, query latency distributions can reveal new information. This sort of pattern where we have two levels, that will be visible from the command line. What won't be so visible is that it changes like this over time. And of course, none of this is visible if you're only looking at an average because you're squeezing everything down to a single line. This is interesting. This is taking that exact same visualization data, and it's highlighting 3 different tables from the queries. And for whatever reason, these queries that involve this table are returning faster than queries that involve this table, and all the slow guys talking to another table. So the point here is that with the right visualization, we can reveal all sorts of new information that would have been difficult to get to. We're discovering things so fast that it's actually, we're still catching up with what we've learned. So that's query latency. The next question is to break it down into components. For a high-level breakdown, we can break it into 2. The time spent on CPU by MySQL and the time spent off CPU. What I mean there is on CPU, you're in the MySQL code executing a query. If you are off CPU, it means the thread is blocked, it's gone to sleep, and you're waiting on another resource. So for examples, you may be on CPU heavy because you're scanning a large table, and that's the CPU cycles. For off CPU, you may be blocked on file system I/O, network I/O, or locks. This high-level breakdown into 2 components is useful because you can direct issues to the right team immediately. If I have slow queries and it's because MySQL is on CPU the entire time, I can direct that to the developers and the DBAs because it's spending time inside MySQL. If, however, I have slow queries and they're off CPU, they're blocked on a resource, I can ask the system administrators to check it out because it might be blocked on file system I/O or network I/O. It may also be blocked on locks, so DBAs may need to look at that one as well. But that's particularly useful because when you have these issues, being able to know which team should pick it up gives you an excellent starting point. MySQL PID slow.d is a script I wrote that does this. It's on my blog. It answers the on-CPU versus off-CPU breakdown. When you run it, and I won't run this one on production because it will print out customer data. Here, this output I've redacted with XXX's. When you run it, it attaches to a process ID, and you give it a millisecond argument, and it will only print out queries slower than that argument. Here I said 100 milliseconds. So it's only printing out queries slower than 100 milliseconds, and there are 2 columns that let us identify the on-CPU queries versus the off-CPU queries. This column is the time of the query latency. This column is the total time that query spent on CPU. So this query here, the query time was 178 milliseconds, and it spent 177 milliseconds on CPU. It was doing a select, a whole heap of things. That's CPU expensive. That's something that the DBAs and developers can look at that query string and figure out. These queries that I've highlighted in a different color, they've taken over 100 milliseconds, but the on-CPU time is very small. There was 111 milliseconds and only 4 milliseconds on CPU. These were rounded down to 0. They've spent over 100 milliseconds off CPU because they're blocked on some other resource or a lock, or MySQL voluntarily went to sleep. This can be a different team that looks at it. We can be looking at file system I/O issues, or network issues, or lock issues. How that script works is it does timestamp deltas like I did earlier, but it also does v-timestamp deltas. V-timestamp is a variable that DTrace has that only increments when that thread is on CPU, which is fantastic. When dispatch command begins, we record the time and also the v-timestamp variable. When that dispatch command finishes, if it was longer than the query we're after, we can do both the query latency and then the on-CPU time On CPU time is the delta of v timestamp. That's how I was able to print out those two columns. So it turns out to be a very, very simple script. 2 probes, a predicate, and a printf statement. But a very useful script. To show what that could look like with a visualization, this has the query latency column in green and the on CPU column in blue. On the left, these queries are on CPU, so we have the query latency equals the CPU latency, so they're aqua. But you can see here they separate out. And we have the query latency time goes up, but the on CPU time stays static. What's actually happening is we're getting blocked. I've dug into this with DTrace more to find out what's happening. And this one is, and this was the same heat map I showed earlier, it's in InnoDB thread concurrency. That algorithm is interesting in that it initially tries to wait for 10 milliseconds, which is a tunable. And if that fails, it then goes into a CV wait. And you can see the effects of that. Here's the initial 10 milliseconds wait when there are, it's trying to limit the number of threads running inside the InnoDB storage engine. So we initially have new threads wait for 10 milliseconds, but when more threads pile on, they start to wait on a CV and get woken up when, wait on a queue and get woken up when needed. That's InnoDB thread concurrency back off. I actually think this has been fixed in Percona. Peter had some good blog entries on this, and there is a patch that hits up the code path that we've had problems with. That's actually an example where we were able to use DTrace to identify that patching is worth it for this customer because they are getting hurt by a code path that we know Percona has patched. Analyzing off CPU time. So it will either be blocking on device I/O, lock contention, or thread sleeps, like if it voluntarily leaves CPU. You can analyze this generically, looking at the time off CPU by the stack trace, and I'll demo this later. I can also use the DTrace shared or syscall providers to look at off CPU time if it's during a system call, which it often is. Or specifically, if I already know that there are functions where we're likely to go off CPU, I can DTrace them individually. For example, in InnoDB, there's the file read and file write, OS file read and OS file write functions.